Thank you. Thanks. Okay, so thank you, Shiksha, again. Our next speaker is Deanna Easley, and she will be talking to us about generalized Kalman filtering for higher order moments. This was a pre-recorded talk, and I understand Deanna is giving us now a summary, and there will be time for Q&A after the summary.
Okay. Hi. Yeah. So I'll be discussing my research with Dr. Tyrus Berry, and yes, and my name is Deanna Easley. All right. So let me first discuss some motivation. So an application of our research is dynamical systems. And so considering the problem of forecasting the chaotic Lorentz 63 dynamical system as shown here, and let's take an initial distribution and the forecast.
Excuse me, but I think at least on my screen, I only see your Acrobat with a title page of your talk. I'm sure you're sharing the same.
Oh, it's not going to the next slide?
Sometimes it freezes, so if you maybe stop the sharing and restart it.
1 sec.
I've had it happen once. And make sure that you share the window that, oh yeah, now I think we can see the Lorentz.
Okay. And 1 sec. Do you see the new slide?
Yes, I think now.
Okay. Okay, thank you. Now where was I? Oh yeah, now focusing in on these distributions, we'd like to summarize these distributions with a small set of points in order to reduce runtime. Currently, we can do that with the Unscented transform, but we want to be able to better capture the variation of the distribution with our own transform. And yeah, so our goal is to generalize the Unscented transform, which is a quadrature that was designed to match the first two moments, so that we can also match higher order moments, namely the skewness and kurtosis. Now, the skewness and kurtosis are tensors, which are basically multi-dimensional matrices, and you can see an image of one here. And we need to find a rank 1 decomposition of these tensors in order to generate new quadrature nodes that correspond to these higher order moments. I'm breezing through here. We were actually able to prove this theorem here, which gives us an effective way to find the rank 1, the tensor rank 1 decompositions that we're looking for. And of course, we can't just throw in these extra points, since that would mess up the existing moments. So we have to do something delicate here. And so we created a whole new set of quadrature nodes, as shown here, and associated weights. And the first three here, the first three nodes correspond to the mean, the next few to the covariance, next few to the skewness, and then the remaining to the kurtosis. And we prove that our ensemble matches the first 4 moments up to these errors that can be made as small as we wish. And now here is what our ensemble looks like. So given this distribution, the black, red, green, and magenta points are quadrature nodes. So the black correspond to the mean, the green to the covariance, red to the skewness, and magenta to the kurtosis. And here we compare our transform to the unscented transform. And as we can see in these cases, our transform in blue performs better on the different polynomials as we expected. And now recall this from earlier when we're talking about summarizing distributions for forecasting problems. The green points here are the unscented transform nodes, while the red ones are our nodes. And you can see here how the red points are capturing the full envelope of the distribution, while the green points are missing a lot. And here are the prediction errors that we get when applied to the Lorentz dynamics. Once again, we see improved estimate of the mean and variance with our transform compared to the unscented transform. And here's the bibliography, and here's where you can check out our upcoming paper. And I'm now happy to answer questions. Thank you.
Thank you very much, Deanna. Are there any questions from?
Yeah. You had a slide, the very artistic one, that looks to me like butterfly.
Oh, this one?
Yeah. How is this related to the original chaos butterfly of Lorentz?
Okay, so this particular one is not related to the Lorentz.
Not at all.
No, it's
only the shape.
What?
Only the shape looks like.
Yeah, it's sort of reminiscent, but it's I'm trying to remember what the distribution we used. It's some nonlinear distribution. I believe used like sine function, and like it was just some random distribution that we did numerical experiments on and happened to come up with this pattern.
It's very beautiful.
Thank you.
Quick question. So one thing I didn't quite get here, both for the standard unscented transform and the higher order counterpart. So the assumption here is that you know exactly the certain moments, like the mean and covariance a priori.
So
when you set up even the standard unscented transform, so we yeah, the mean and the covariance are given as input data, right?
Yeah.
But if we are in a data sort of a simulation environment where we, let's say, have a particle method, or we only know these two, you know, the mean and the covariance only approximately, does that introduce issues here, or how do you envision applying this in a setup where maybe you don't know the mean and covariance exactly, you only have approximations of it?
So so basically, when we're given a distribution, these transforms can be used to approximate the mean, covariance, and then with our transform, the skewness and kurtosis. So what we're kind of doing here is that we're showing that, oh, this actually matches, this approximation matches what the real mean and covariance are. That's sort of the idea. that makes
Right. I understand that. I was trying to put it in context in situations where you don't know maybe the mean, exactly right, the mean, the covariance.
Can I comment a little bit on this?
Please.
yes.
So I guess if I may rephrase what Dimitri was saying, is like, okay, if you apply ensemble data assimilation with this unscented, right? So on every step, you probably processing using your dynamical systems to propagate the particles, yes? And then from the particles, you are going to compute empirical mean, empirical covariance, empirical third order moment, empirical fourth order moment, and then you just fit it using your current method, yes?
Yeah.
And then you go again, right? And then you repeat, you go again, right? So I guess what Dimitri is smelling is there's a blood here, meaning that, okay, you're computing empirical statistical moments. The error on that, on such, you know, empirical statistical estimation, right? The Monte Carlo error here should, you know, basically goes really bad with respect to the ensemble size, right? So what I really mean is like, if I have like, okay, let's say 2-dimensional or 10-dimensional system, n-dimensional system, right? It's supposed to require, you know, an ensemble size of variance of the mean divided by root n to get a good estimation for the mean. But for the fourth order moment, that's going to be like variance of the x to the fourth. That's probably going to kill you, right? So that means the ensemble that's needed will be like immensely, really high, right? In order to fit the third and fourth order moment, right? Because otherwise, if your empirical third and order fourth moment are bad, then you're basically fitting something really bad, right? Is that maybe clarify? Or am I misunderstood your method?
So if I am understanding correctly, you're basically asking if the dimensions of the moments that we're dealing with is too high, like what will happen to the errors?
Yeah, of course, right. That will also relate to that. But even let's just say, you know, 2-dimensional problem or 3-dimensional problem, right? You probably need a lot of ensemble size in order to get a very accurate estimation of third and fourth order moment to be fit to your unscented transform or this modified transform. Is that correct?
Well, I can say for the 2-dimensional cases, which we've been experimenting on, not actually, so not, there haven't been in our experiments that we needed to use that many points for, for the ensemble. Like it typically was maybe for, let's say for the higher order unscented ensemble here. So remember like J and L. So J would be the number of the eigenvectors for the skewness, and L for the kurtosis. We typically had around 11 for both of them. And so not actually a lot for the 2-dimensional case. And it typically was fairly accurate and pretty fast. But we haven't really gone, looked at other dimensions yet to really say.
Okay. We have a question on the chat. Would this technique be useful in picking parameters for an ensemble simulation?
I'm not sure I understand the question actually.
I suppose maybe, you know, I don't want to speak for the person who asked. I don't know if Hugh is still here. here.
Yeah.
I think oh, it seems to be here.
Yeah, I'm not sure what ensemble simulation is.
Maybe it means, you know, if you're running a climate, oh, there's a, we would like to have our ensemble model in the system well, but use few runs. How best to pick?
Oh, okay.
Run.
Okay, so that's built into the, oops. Yeah, so that's built into the a sigma point. So we designed them so that the parameters are picked up optimally. So we're yeah. So it's in the weights, basically, how we have the weights set up with these constants, alpha, beta, gamma, and delta. It basically alpha, beta, and gamma and delta can be anything that's set up in the beginning, like alpha can be 1, for instance, and the way this is set up is that it's perfectly balanced so that it runs optimally. But oh yes, and here alpha and beta specifically are designed to be minimized as much as possible, because this is what we calculated for our empirical mean covariance, skewness, and kurtosis, where we get these error terms. So because we want these error terms to be as small as possible, we set up alpha and beta to also be small. I hope that answers that. Any other questions?
I don't see anything. Maybe I have a last quick one. What in your plans for this are now to put it in the context of a Kalman filter? Is that?
Yes. Yes, exactly. Mm-hmm. So we're at the like the first stage of the I'm trying to remember the term. I think the initialization stage or assimilation stage. Sorry if I'm getting them mixed up at the moment, but yeah, we're going to be working on the Kalman filter, applying this to the Kalman filter.
Okay, I think I don't see any further questions for now. So I'd like to thank again Deanna, and as well as Xixiao for this very nice first part of our Minisymposium. So we will be resuming again at, let's see, make sure I don't give the wrong information here, at 7 for the second part. And as I mentioned in the beginning, there is also MS12 in the meantime that starts in half an hour and could be of interest on similar topics what we're discussing here. So yeah, thank you everyone for joining us today, and we hope to see you again in a couple of hours.
Mm-hmm.